this picture's already getting a little bit cluttered, so let's take it out of this context and simply redraw it with the rectangle slightly bigger, and we're not going to worry yet about the delta x. Let's just worry about the effect of delta y. So we have a point x0, y0 somewhere in the xy plane, and since we're now talking about a graph in 3 dimensions, we're going to include the y coordinate of that point. So there's your point in the xy plane, x0, y0, 0. Z is 0 in the xy plane. This point is going to represent x0, y0, f of x0, y0, whatever function f is. We evaluate it at x0, y0, and we get the value, and that's how far we go in the z direction. There's a point on our graph. Similarly, we assume a change in y of delta y, and this moves us to the point x0, y0 plus delta y, 0 in the xy plane. Evaluating the function at that point, we get f of x0, y0 plus delta y as the z coordinate, x0, y0 plus delta y as the x and y coordinates. Presumably, in most cases, for most functions that we'll be considering, there will be some change in the value of f. I'm going to draw a horizontal line here, just to indicate that this line is at right angles to the z direction, to the k vector if you wish. The change in the function is this, so that we could indicate, well, let's move to a slightly different color here. And first of all, this isn't necessarily the way the graph of the function behaves between here and here. It might or might not be a straight line. However, we expect that for a well-behaved function, if delta y is small, then the graph will be approximately straight. This gives us a triangle, and if we draw that triangle off to the side and think about its dimensions, this dimension of the triangle is going to be what we call delta f, which equals f of x0, y0, f of x0, y0, and that's not right, and I'm a little distracted because I didn't leave myself enough room here. So I'm going to pretend I didn't do that. And let's come down here where we have a little more room. I'm just going to move this triangle down here. Okay. Now, the height of the line here is f of x0, y0 plus delta y. The height of this is equal to the height here, which is f of x0, y0, and the difference here is f of x0, y0 plus delta y minus f of x0, y0. So we're going to have a delta f here, which is going to equal f of x0, y0 plus delta y, this height, minus this height, which is f of x0, y0. And that delta f arises because of the delta y here. The slope with respect to the y direction it's delta f over delta y equals f of x0, y0 plus delta y minus f of x0, y0 divided by delta y. This is a familiar difference quotient. Represents the slope, and as we expect, this represents a kind of a derivative. So I'm going to say that as delta y approaches 0, we're going to consider that in a minute. Let me make one more comment here. This is the average rate of change of f with respect to y over this interval. I'm being a little vague about what I mean by this interval, but conceptually this slope represents an average rate of change in f divided by change in y. So as delta y goes to 0, the delta f over delta y approaches a limit a limiting value. Now we're assuming that your f of xy function is one for which this does occur, that the delta f over delta y does approach a limiting value in the vicinity of the point x0, y0, we're going to call this f sub y of x0, y0. This is the instantaneous rate of change of the value of the function with respect to y at the point x0, y0. So this is the instantaneous rate of change of f with respect to y at the point x0, y0. And we're going to give this a name. We're going to call this the partial derivative of y of f with respect to y at this point.